Good evening, everyone. On behalf of JPR Institute of Technology, I welcome you all for the Day 4 Faculty Development Program on Contemporary Research Trends, Innovations in Materials and Technology. It is my great pleasure and honor to extend a warm welcome to our distinguished guest speaker, Professor Dr. Panayotis Kiratsis, who has joined us from Greece. This FDP aims to foster collaboration, innovation, and knowledge sharing among faculty members, and your participation symbolizes the importance of global perspectives in education and professional development. We are excited to learn from your experiences and insights. And also, I want to express my gratitude to our Managing Director, Dr. Maria Wilson, Principal, Dr. G.R. Suresh, IPSC Director, Dr. Shenbahayalil, Academic Research Dean, Dr. Shantini, for their constant encouragement and support to conduct this program. Before we start, I would like to introduce our distinguished guest speaker today, Dr. Panayotis Giratsis. I invite Ms. Marlene to share the profile of Professor.
Good evening to one and all present here. It's my privilege to introduce our distinguished chief guest, Professor Dr. Panagiotis Kratsis. He is the head of the Department of Product and Systems Design Engineering, University of Western Macedonia, Greece. He is the director of the Institute of Traditional Architecture and Cultural Heritage, University Research Center, Temenos, and the director of the Computational Design and Digital Fabrication Research Lab. Professor Dr. Panagiotis Kouratsis received his PhD in the area of CAD-based manufacturing process simulations from the Department of Production Engineering and Management, Technical University of Crete, Greece. He holds a graduation in mechanical engineering from the Aristotle's University of Thessaloniki, Greece, and he received his postgraduate degree in automotive product engineering and postgraduate degree in CAD/CAM from Cranfield University, UK. He has been involved in a number of industrial projects and he has a great deal of expertise in both the design and the manufacturing aspects of product development. His main research interests include manufacturing, machining, CAD/CAM, CAE systems, computational design, additive manufacturing, CAD-based applications, product design, reverse engineering, and prototyping. He has published more than 20 books and more than 190 papers in scientific journals and international conferences. He acts as a member of the editorial board and reviewer to numerous scientific journals and holds 12 industrial designs and 2 patents registered within the Greek Patent Office. We welcome you, sir.
Thank you very much. Thank you very much for this introduction. I would like to thank you all. First of all, the organizers that they gave me this opportunity to present the results of our research. And at the same time, all of you that you spend this late afternoon with me in order to see what things we are doing here in our laboratory, and let's explore what kind of collaboration we can establish from today onwards. So my presentation is going to be about computational design and 3D printing applications. And I'll try to make it more close to practical issues. And hopefully the presentation is going to give you a better understanding of the research that we are doing here in Greece. And I'm really glad that you were able to pronounce my name very well, which usually is not the case. And that's why usually my friends and my colleagues, they call me Pan with my first name, which is much easier. Thank you very much, and I really appreciate that. Let's see the agenda of our today's presentation. I'm going to talk about computational design and digital fabrication research lab, the one that we have established in our own university here, and I'm directing this laboratory. Somehow, I think I'm going to give you a better understanding of how we can create CAD-based applications or computational product design applications, and how all these things that we are going to design or we are going to model, they are supported by 3D printing manufacturing as a process. At the end, I have something which is closer to machining and material technology, which is simulation using finite elements analysis. But again, the way to run all these simulations are based on CAD applications. Let's see some of the pieces of equipment that we do have in our laboratory. We have a number of CNC machining centers. We have a 4-component dynamometer, surface roughness measurements equipment, tensile compression bending testing facility. We have a variety of 3D scanning processes, 3D printing technologies that we are using for our research, and the prototyping of the product that we design, laser engraving and cutting, and we have one of the largest probably in the area here, large format inkjet printer. As far as it concerns the piece of software that we use, we have a variety of CAD/CAM and CA pieces of software like SolidWorks, AutoCAD, Inventor, and so on. We use for linear and non-linear analysis using finite elements usually, ANSYS and Deform 3D. We have a separate CAD software for packaging design, and extensively we are using Rhino 3D and Grasshopper, as we will see later on. Let's start with some small introduction about CAD-based application programming interface. In the design and in manufacturing is something which is relatively new as a topic. So what we do the API in order to provide the user with a number of possibilities that lead to productivity enhancements. At the end of the day, we are programming the API of a CAD system in order to achieve several issues like automatic operation of various CAD features of a CAD system, to be able to interact between different software modules that we have built or they are already built by other manufacturers, or even to accommodate a series of engineering calculations. Of course, someone will say that there are a number of highlights, and usually in the presentations we stick to that, like enhanced productivity, improved work time allocation, quick and easy error recognition during the product design cycle, reduced times, as we would like to have. The time that we save, we can use it to something which is more important to do during this period of the design of the product, better implementation of design ideas, or better handling the product development. But unfortunately, there are some drawbacks in this direction. First of all, it requires understanding of computer programming. As we know, because my background is mechanical engineer, we don't like programming. So usually the engineers don't like programming, especially people that they come from the mechanical engineering background. But if we pass to that, then we have sometimes the benefits are not worth the investment in time and resources. And the last one, which probably is the most important, is the lack of thorough training guides. Usually the CAD manufacturers, they don't actually provide access to this kind of tools, like the language that we can use in order to build our own tools. So it needs a bit of effort to go towards this direction. Let's see what I mean when I say a CAD-based design manufacturing tool. What we try is we can create various modules that can be combined together, and we can build several software tools. In other words, what we can do is we can build a platform that has a lot of tools, and we can actually design different stuff. And in this case, we can facilitate usually time-consuming tasks. And all the time, we can extend the functionality of this platform by using the code that is available for us. Let's say I have decided to show you a simple example like the 3D designer. In this case, we have the layout from the user's point of view, and you can see that we can do a fully automatic selection of different object types. We can have some topology entity selection. We can highlight this kind of selections, and we can go towards along the hard disk that we are using. In other words, what you see here, we have the part itself, the model of the whatever we are designing, and we can select different entities. We can highlight them, but mainly the main idea is to be able to select automatically this kind of entities like faces, edges, and so on. We have different other tools like we can automatically create different features like chamfer, fillets, different holes, and so on. And you can see here there are different layouts that we give to the user, and we can actually select automatically where do we have to do a chamfer, a fillet, or giving the position of a hole, and what kind of properties do we want to give to the hole each time. Like I think this is a very good example, like the flange. Here, we are able to select what is the standard that we want to follow in order to build the model of this flange. We give the dimensions, the holes, the number of holes, the hole diameters, and so on, and the standard that we have to follow in each case. We get the CAD model of this flange, in this case it's a flange, and then we are able to have not only the model itself, but we are able to provide some automatic generation of basic engineering drawings. As you will see on this slide, we have some typical views of the mechanical drawings from the assembly or from the part point of view. We have the bill of material, and we have a complete engineering drawing set in order to help the manufacturer to actually produce this kind of products. What about if we need to do it a bit differently? And usually this is the case when we have some geometries that they are more unusual, let's say more complex. In this case, we have to change the tool that we are using, and we have to go towards some visual and textual programming language, which you will see later on what I mean with that. We programming, and the screen is something like that. There are different boxes. We call it spaghetti, and we have different lines, input and outputs, and we have to connect all these in order to run the program. And this is what we call visual programming. Inside each box, we have some kind of code, which is usually written, in our case, is written in Python, in order to incorporate the functionality that we would like to introduce in our application. I have some examples, some simple examples here, like if we have a plane and we have an object, which the geometry can be whatever we want, we can have this script. It's a Python script. There are some parameters that I will skip it. I will skip the details of it. And then the output is going to be having this geometry sliced. And depending on the values that we will have in each parameters, we can have different slices over here and different results. And what we say is, what we design is a family of products, because we are able to have a variety of alternatives. And what do we do with that? We can use a CNC laser cutting and engraving machine in order to actually manufacture that, because we don't only have the slicing, but we have all the geometry information, and we have all the drawings available. If we would like to build something which is a bit more difficult, let's say, we can go here. we can design a surface, whatever surface we want, and we can have two planes. We run a piece of software, a piece of code like the one that you see here, and this gives a result, what you see here, a very funny, unusual structure, which can be used in a variety of areas like architecture and so on. The main idea here is that we are able, depending on the values that we select over here for each parameter, we can have all these alternative designs. And when we have all these alternative designs, we can select which one we like from the aesthetics point of view, from the technical characteristics point of view, and so on. And we are able, again, to use some CNC laser cutting technique in order to manufacture it, either the product itself or the prototype in a scale. What about if we would like to insist a bit more on using the visual programming tools? As you see over here, we don't have actually Python piece of software, of code. We have all these little boxes connected to each other. And we can build a simple geometry. For the sake of the argument now, I'm putting something simple. And then we can apply different algorithms over here, some patterns and so on. And depending on what are the values of all the parameters, we are able to have all these parts. And then at the end of the day, we can 3D print it, this kind of plastic structures, in order to have them available. Let's go to something which we start now getting to something which is a bit more tricky, something more difficult. What about if we would like to have a graphical algorithm for the design and the assembly of a DIY desk workstation? You see here, there is an image, but I'm going to explain it a bit in more details. We can have this DIY desk workstation. We can have over here to design by ourselves, and we can set all the parameters, and we have alternative designs. And at the end of the day, what do we get? As we will see later on, we get all the drawings, the mechanical drawings for manufacturing the desk workstation. And the most important is we have this leaflet, because when we buy a DIY product, we need a leaflet in order to lead us how to assemble it. And all this, depending on the parameters that we change, we have the customized leaflet that is built based on the parameters that the user is using. Like in this case, as you can see, we have the furniture preview, we have the different parameters here changed, and we have the export of the files. We have the code which has this it's a bit complicated, and there are a variety of commands over here, but at the end of the day, when we run the code, we get as an output the product itself. Over here there are the details of that, but I'm going to skip that for now. And at the end of the day, what do we have? We have the selection from the designer's point of view, what the designer wants, all the dimensions over here, and then we have the product. And then out of that, we have the drawings, we have a bill of material, we have the cost of the DIY, and so on. We have a design alternatives. Every time we change the different parameters here, we have an alternative product. While at the same time, from the customer point of view, you get not only the drawings which the manufacturers need, but in this case, you get the assembly instructions of the tech of how to actually assemble it at home. Let's go to something that might look more interesting. Sleeper modeling. A number of publications that we have is on wearable design. In this case, I'm going to present you some sleeper modeling and prototyping and what we have done with that. But as you will see that there is a lot of engineering behind that, behind the scenes, although at the end of the day, what we have designed, the sleeper soul. In this case, the main aim of research is to design a customized pair of slippers for the user. In this case, what we need is a 3D scan model of the foot. Hopefully, you can hear me well. Can you hear me well?
Kindly Participants, kindly turn off your audio mode, please.
Okay. So what we need is to have let's say two directions, some basic data, the 3D scan of the food, each one of the feet of the customer, and the plantar pressure from each foot that we get when the user is standing on top of the machine. At the end of the day, what we want is to have a 3D printing of the solution of whatever slipper we have designed. Uh, if we skip a bit the technical aspect, I should say that usually we work in 2D initially in order to be able to build the algorithm that is going to connect the pattern that we are going to use every time. And after we are able to control the pattern and how this pattern propagates in the 2D geometry, as you can see it over here, then we work on the 3D, as you will see it on this slide. And in this case, we have three strategies, let's say three different pattern geometries that we use, the first, the second, and the third. And you can see that this is alone the pattern itself, the geometry, and then how this is transferred to the 3D geometry. Let's say that in our case, we have a customer who is going to provide us with a foot analysis, the plantar pressure of its own foot. So we have this as an image. Then we are able automatically to read the areas that we have a high pressure or a lower pressure. And then we separate these areas here automatically. And at the end of the day here, we are able to say that in these areas, these 3 points that we have the high pressure, we can increase the density of the material used, and then somewhere outside over here that the pressure is lower, we can decrease that. And automatically, again, we can create the 3D view of the sole of the product itself, and this is the deformed shape depending on where are the areas of the high pressure and where are with the low pressure. And we have tried that by having them in the three separate geometries used. And you can see over here that we have the initial mesh. And over here, the mesh that comes when we have a higher density in the areas that we have high pressure based on the data that we had initially. But this is not the only thing. We would like to have the 3D scan of the food itself in order to be able, at the end of the day, to build a product which comes and it's customized for this specific customer. So we are able over here to build the slipper which belongs exactly to this customer. And at the end of the day here, you can see the three different variations of the geometry used for the sole. And how we can actually make this kind of products. And now we come to how we are using 3D printing. In this case, we have a relatively big 3D printer, an FFF 3D printer. And what do? We actually print these slippers, which are dedicated to the user who gave us the plantar pressure and the 3D scanning model of his feet, both the feet. And then we print them out, and we were able to provide pairs in order to use them. In this case, up to this stage, what we have done, we had an early evaluation, and we tried to measure how well we have built these slippers based on the comfort, the stability, and the pressure uniformity. And you can see over here the results when we have a standing position, a normal walking position, or a fast walking. And you can see if the comfort is quite good or not, the stability and so on. And we have the results for each one of the geometries that we have studied. And you can see in this case that the second one is supposed to be a more effective, efficient, more comfortable for the user. But this is the way to actually design something, automatically design a customized product for the user. And at the end of the day, you can get the product by using the 3D printing technique. From our side, what we are trying to do is we are trying to have all these advantages coming from the Industry 4.0 principles to use some CAD-based programming, 3D scanning, 3D printing, food pressure data analysis, and so on, and try to incorporate new methods, new materials, new digital tools in order to have the customization of the shoe-related products. And all these, I think this is the magic word, to be automatically done. So what we design are integrated applications in order to have customized products. And in this case, we are able to provide alternative designs for each solution, because sometimes the user needs to see the product from the geometrical point of view, but from the aesthetics characteristics as well. What about if we go to another application like modeling and prototyping, some kind of something that comes from fashion? Let's say that we would like to have this person here. We can measure different dimensions on top of the person, and then we can process the data and have as an output this 2D geometry. And this 2D geometry comes directly by having this visual code over here. And depending on the parameters that we are changing, we can have, as you can see over here, different geometries depending on the customized development of the product, depending again on each customer that we would like to offer the product itself. And then there are some alternatives that you can see from the front or from the back view. In this case, again, using the code, you can have all these alternatives. And depending sometimes on the aesthetic characteristics, the customer needs to choose which one fits better or looks better and so on. So we have all these alternatives available. And we have all this data input, and you can change, you can slide over here the different values. And then by sliding all these values here, you have the alternatives 2D patterns as a result. And then, as you can see over here, by changing the different values, you can have the variety of alternatives on the product to be built. At the end of the day, we are using some 3D printing technology, an FFF technology, again on the same 3D printer, which is a large size printer. It's the size of the product that we can build are 600 millimeters by 600 by 600. And we are able over here with a flexible filament to build the different geometries of the pattern. And then we need all these little components in order to be able to assemble them and have the final product assembled and to be wearable on the customer himself or herself. And as you can see over here, we have all these dimensions which lead to a customized product for the customer. Nowadays, we are preparing a new application for creating more things, more wearable products. I will transfer you now to, there is a big question now. When we are actually printing all these materials, what kind of parameters do we use? What kind of values do we use for building all these materials and all these products? And then it comes to, okay, we are designing all that. We do everything automatically. We have access to the printer and so on and all these nice pieces of technology. But what about if we want to actually build something which is durable, something which is lighter, or something which is softer and so on? So in this case, we have started maybe the last 18 months to work on the different structural characteristics of the materials using the FFF technology, 3D printing technology, in order to be able to optimize the use of the parameters that we have in its time. Because we have published this paper maybe 6 months ago, I took that's some of the things some pictures of the things that we have done. In this case, we are presenting some research that examines the structural performance of the ABS polymer. And we are using a shallow neural network in order to model how well this performs and how we can do the fitting of the performance of this material. In this case, I would like to say that we are not actually measuring only the strength of the material, which usually this is the case when we have different applications published. We have decided to use the strength to mass ratio because for us it's very important something to have the strength in order to build the product, but at the same time to be as light as possible as it can be. That's why our publication in this area, the last one, the latest one, was about the S to M ratio. So the strength to mass ratio, to have as big strength we need for the material, but as low weight, as less mass we can use for that. In this case, we have created the design of experiments set up. It was based on the central composite design. We have 4 structural characteristics and 3 levels for each characteristic. The total amount of experiments given by the central component design was 31 tests, and we had double doing the test all the time, so we had 62 specimens in this case. You can see our printer over here, the specimens. All the specimens were numbered and were weighted over here in order to be able to know what is the weight of each one of it. And then, as you can see over here, we did the tensile testing. And then we have created the neural network model with some hidden layer over here. As you can see over here, the structural parameters used are these 4, and we have incorporated here inside the structure, which can be incorporated inside the geometry. And apart from there are 3 levels every time, and these are the fabrications used for actually creating all the specimens. We have followed the STM D638 standard, and the geometry is the one which is given over here, and this is the picture of the specimen. Depending on the layer, if it is 0.1, 0.2, or 0.3, you can actually see how the inside of the specimen is, or depending on the infill characteristics, again, you can actually see here if it is 20%, 50%, or 80% infill. Again, you can see over here we have more material, or the line direction, if it is 0 degrees, or 45, or 90, which is horizontal in this case. And then over here, we were able to measure what is the performance of different patterns, like the grid, the triangles, and the honeycomb. We have been using the 3D printer, as you can see it over here, which is quite big in our case. The specimens, we have fabricated all of them. Doing the testing, using the Instron 3345 that we have in our laboratory. Some pictures over here, the time that the specimens break, how we manage to weigh them. And as you can see over here, we have the accuracy of 4 decimals after 4 decimals for each gram. And when it comes to the neural network here, as you can see, you have to go to some kind of trial and error way. And in this case, you can see that the R value of the 6 nodes is supposed to be the most well performed, although this is not always the case, but this is something that has to do with the neural networks. This is the neural network that we have been built in order to incorporate the 4 inputs to run the neural network. At the end of the day, to have the output, which in this case, the output is the S to M ratio. If we go towards the mass, we had to do the data normalization. I will skip the details of it. And this is the function that gives the S to M ratio in each case. And these are the H1 up to the H6, all the values of its constant that we need in this formula. And then there were some evaluation, some network evaluation for training and validation. And again, everything was supposed to be very good, and all the experiments, they were very well fitted by using this neural network that we have designed. And as you can see over here, the different parameters, how they affect the S to M ratio. You can see over here how the inclination here is very rapid. In this case, I will say it now that it goes down and then there is some constant value over here. Again, the inclination is negative in this case. And for the, depending on the structure that we use inside the specimen, over here you see we have different application, different way of behaving. And if we try to compare, to do the comparison between the predicted and the experimental results of the strength to mass ratio, this is the output, and it seems like what we have designed, what we have calculated, it fits quite well the experiments that we had completed. For the conclusions, more or less is what I have already mentioned to you. I will skip them for now. And I will go to something which probably from the mechanical and the manufacturing point of view, it might be more interesting for some of you. How can we use the CAD-based modeling the CAD-based inserts in order to use them in a nonlinear finite element analysis in machining? We will see some of the details of that. We come back now to the CAD-based automated design of FEA-ready cutting tools. In this case, we have the opportunity to design either rhombic geometries or square geometries. And we can put over here different parameters. And in the end of the day, this application gives the output, the geometry of the tool. You can see over here the picture of a tool, the micro geometry, which is over here. At the same time, how this micro geometry is applied to the CAD model. I'm sorry. Over here, we have the application. Depending on the different selections over here, you can have a variety of cutting tools. I have prepared a little video here. It's not going to be long. It's only 30 minutes, 30 seconds. So you can see over here how we are selecting the different parameters from the menu. The user is doing that. At the end of the day, we are able to provide the design and manufacturing engineer with the tool to be used later on for the finite element analysis. As you can see here, the time that we need in order to build this kind of geometry is quite limited, and we can change the different parameters and have another tool. I'm sorry for that. So I think you got the picture that it's something that happens quite quickly. So we have prepared this kind of automated design of the turning tool in this case. And what about, can we actually test these models using some finite elements analysis? And in this case, we are using the deform 3D piece of software in order to run this kind of analysis. I will skip some of the details about turning and so on. The 2D analysis, which usually is the case, enables the use of analytical rigid part that reduces calculation time. It simplifies the mechanical problem and is ideal for preliminary simulations. But in our case, what we prefer is the 3D analysis, which produces results closer to the real conditions and uses the full geometry of the tool. It is ideal for complicated simulations. You can see over here how our application is creating this assembly and brings everything together in order this model to be ready to be inserted and incorporated into the FEA piece of software. And you can see from different directions and the different tool holders what kind of selections we can have in order to be able to simulate this manufacturing process. And then we can calculate not only the forces, but the temperatures as well. In this case, this kind of geometries, if it is a rhombic geometry, we can use it like that. Or if it is a square geometry, we have all these parameters, and you can see the micro geometry needed to be defined. Different tool holders, we need them in order to position them correctly for the FEA analysis model. This is the workpiece, the part that we need in order to make the simulation. And as you will see over here, this is the complete part, but we don't actually need all of it. We get only a piece of it, like this one over here, because at the end of the day, the temperatures and the forces that are going to be developed are going to be constant in this case. So we can save some time in the computer time. And in this case, the simulation setup is like that. Over here, we have a tool. We have the workpiece. The workpiece in this case is broken and meshed into small pieces. There is a 7:1 mesh size ratio and so on. There are some tips that we give over here, like for the tools, 4:1 mesh size ratio is needed. I will skip these details here, but we have to set up what is the material and fracture modeling. In our case, it can be a Johnson-Cook model because it's a non-linear change of the material, or the material properties in this case, the friction, the Coulomb law, and what is going to be the friction coefficient, 0.6 in our case. In this case, we have to set up all the boundary conditions for both the tool itself and the workpiece, and then run the application. And as you can see it from a different view, this is how we create the chip, how we simulate the chip which is produced when we actually manufacture the material. You can actually see over here the steps. These are all the steps that you have to run each time. For each specific step, you have to run again the model. That's why the time needed is quite big, quite large, significant. And then these are the results in pictures, and you can see, depending on which setup we have, this one or the other, and what is the outcome. These are the different cutting forces developed, and something which is quite important and so quite significant is the temperature distribution, again in the same experiments. We have run all the experiments needed in order to be able to build this kind of models. Again, over here you can see that the temperature is built depending on the time needed in order to do the analysis. You can see over here the temperature increases and is stabilized quite high, or over here is exactly the same. And you can see on this case over here the chip and how the chip is the chip propagates. And again, this is the temperature distribution in images in order to be able to judge what is the best solution for the tool and so on. I will not go through the results of that. I would like to thank you for your attention, and hopefully I have created some questions for you, or maybe some research opportunities and some collaboration opportunities for the near future. Thank you very much.
Thank you, sir, for delivering such an insightful and engaging talk on 3D printing during this FTP. Your expertise and knowledge you have shared are invaluable, and it has been a privilege to learn from your experience. Your presentation not only highlighted the innovative advancements in 3D printing, but also provided us with practical insights. We sincerely appreciate the time and effort you have invested in being with us today. We look forward to future opportunities for collaboration. Thank you once again for making this session truly enriching and memorable. Thank you very much, sir. Thank you
Thank you
for
very
your
much all.
acceptance also, sir. Participants, if you have, this session is now open for discussion. If you have doubts, kindly ask.
If you don't have now any question, you can use my website, which are all the details of the work that we are doing. And I'm writing that on the chat. And you can use that, my email and so on. And even in the future, in the near future, we can discuss about opportunities for collaboration, research collaboration, authoring or editing some papers and so on. Keep it in mind.
Okay, sir. Thank you so much.
Thank you very much. It was a privilege for me to be here with you all. And I'm really honored to have all these participants, almost 150 people, being with me tonight. I really thank you all.
Thank you once again, sir. Feedback form posted in the chat box. Kindly fill it.
I can see that from Dr. Dennis, there is a question about the achievement of 3D printing technology and what it's expected to emerge in the next decade. From my perspective, I wouldn't say a lot about the technology developed because I wouldn't consider myself being a material expert. But because we are using 3D printing technology, as you saw, in order to be able either to prototype different products or to build products which can be built only by 3D printing, because in this case, when we have very unusual geometries, very complex geometries, which are the result of computational design, it's only 3D printing that can give you the outcome in one-to-one scale, and the production of customized products can be built only with the 3D printing. So from my point of view, probably the technology will go not only towards new materials, but I think it will go towards building models in lower time. So building different models or different geometries in less time. Any possibility of making 15 slipper? We cannot actually build 15 of the same one, because for the same person, it's only one pair that we can build, or 2 or 3 pairs, depending on the geometries every time we are using. Like you saw that we have 3 alternatives in our case that I presented. But this is a very good opportunity when you want to design and manufacture your own slipper or your own wearable or whatever you want, which is going to be customized only for the user, which is going to participate in this research. So it's something which is quite nice to have customers or users that would like to have his or her customized product. As far as, apart from the polymers, as our friend here asked, lately we have started working on composites, and we have prepared 2 papers now. We are expecting them to be published. And the last summer, last 3 months now, we are working on polymers which inside they have some powder of metal. In our case, what we are studying now is polymer together with copper or different kind of applications that we can have inside the polymer to have powder of metallic or other material. From our point of view, again, I'm not I wouldn't like to go towards 3D printing technologies, because I'm not expert in that, but we definitely are using the AI, artificial intelligence tools, in order to build products which are later on printed either as a product or as a prototype using 3D printing technology. So yes, to answer, we are heavily involved now the last maybe year with AI tools that are providing uh, extra capacity and extra capability to our team in order to have more complex or more unusual geometries to be built.
Participants, if you have a questions, kindly post it in the chat box or ask sir directly.
And because I saw yesterday some of our participants, they would like to have a PDF for the presentation. Do you mind if I put now the file on the chat? Or would you like me to send it directly to you, Professor, and you can share it with the rest of the participants?
Professor Pan, thank you so much.
Thank you, Dr. Dennis. You can call me Pan. Pan is my first name, so you can call me Pan directly. Thank you very much for the opportunity you gave me, and you were the person that you did contact me for this presentation, and I would like to thank Professor Sarogini for accepting my presentation being with you. Thank you very much all.